Spacetime cube and tangible interaction. Very long title.
Thank you very much. So good afternoon, everyone. Before I get started on the actual paper today, I just want to acknowledge that I'm actually presenting on behalf of Seung, Youb, Ssin, first author, who unfortunately couldn't make it today, but the majority of what you've seen today is the result of Shin's hard work. I want to start off by kind of talking about the motivation, how we got here today. Our research is funded by a national research organisation that's focused on addressing the big data needs of Australia's national security agencies. And a part of our role in that was basically to go around, talk to all the different organisations about their points of pain, their problems, and see how we kind of address them. One of the problems that came out of that was essentially this. So there's an organisation that's dealing with geographic data sets, and got access to an open source data set that's effectively real-time GPS positioning of all the ships that are out at sea. Now, from a national security standpoint, from a border protection standpoint, this is great. The issue is it's self-reported. So whilst we can figure out where we need to potentially allocate resources to, how do we actually validate that the data that we're making those decisions on is actually correct? Turns out that's easier than you may think. At least once every 24 hours, we have a satellite pass overhead. What that satellite can do is then extract where light is being emitted from in the middle of the ocean, figure out obviously something's got to be in the middle of the ocean that's emitting that light data, and then start to extract individual data points, and then it now becomes a problem of having to associate these discrete data points for where we have light data coming from back to the continuous trajectory data that we have that the ships are reporting. Turns out that if someone's doing smuggling or whatever it may be, they won't necessarily just switch off the transponder and then turn it on in the future. They'll actually spoof the data as well. So whilst if you're looking at the data set, you'll get a continual trajectory for that ship. It will just be that the ship is lying about where they are. So the initial direction is we wanted to look at how can we reduce the complexity of dealing with these multiple data sets. We've got one that's trajectory, one with these discrete points. And then how can we reduce the uncertainty present in the associated 2D visualizations? So basically, what they were doing at the moment was dumping it into a 2D map like you're seeing on the right-hand side there. The obvious issue being that if you have multiple traces and we've got this one green light data point in the middle, how do we know which trace this is actually associated with? So obviously visualization in a geotemporal space is not new. What has changed obviously over the last few decades is the capabilities of the digital tools that we have. So one of the representations, Spacetime Cube, is not our work but referencing prior work. Effectively, for the space-time cube, what we can do is represent latitude and longitude, and then up the perpendicular y-axis, z-axis, whatever your coordinate system is, represent time. So what we effectively end up with is entities that are moving over geospatial space, but then as they move up, we essentially end up with a spiral in the air, as you can see on the left-hand side there. The evaluations that have been performed on the space-time cube actually show that it can help provide users with a deeper insight for trajectory-based data sets. That said, it obviously doesn't have to be just for trajectory-based data sets. You can also visualize discrete points as well. The primary issue when we use these kind of representations is when we create these 3D views and we put them back on a 2D display, we then have issues with occlusion, perspective, and all the traditional issues that we have with 3D on a 2D display. So whilst it's difficult to really ascertain the relationship between that single light data point and the two trajectories on the left-hand side, the second we put that into the space-time cube on the right-hand side there, we can actually see straight away that that light data point is associated with the top trace. So to enable these kind of insights, we wanted to provide a space-time cube that actually overcame the previous limitations of showing it on a 2D display. Obviously, this being IEEE VR, augmented reality has been shown that we can start to overcome the occlusion depth perception issues by actually taking these 3D representations and then putting them in a 3D display rather than showing them on a standard monitor. And then when we sat down to figure this out and said, okay, we want to put the space-time cube, we want to put it in AR, do we go down the tablet-based route, do we go down HMDs? Again, going back to the literature, Buck et al. Demonstrated that if we use HMDs over desktop, it can actually aid user comprehension because we're presenting the information relative to the user's field of view rather than the tablet's field of view and them having to manually translate that relative to the user. But we still need some kind of map. So whilst we could use the space-time cube to represent all the data that we have, at the end of the day, like Maxime was saying, it's going to be focusing on some kind of details on demand or some kind of filtered view. So how do we explore the whole data set? Again, going back to the problem domain and the end users that we're dealing with, it turns out that people that work in the geographic domain really like maps. And I don't mean maps in terms of the 24 inches in front of you. I mean like a big table, rolling it out, everyone standing around in a collaborative sense type map. So our approach was to use the AR Spacetime Cube in conjunction with a tabletop map display. What this enables us to do is as closely recreate, kind of literally rolling that map out across the table as we could, and then have the Spacetime Cube interacting with it as well. If we go back to the very basics of visualization, we need 3 steps. We need the overview first, we then need some kind of filtering mechanism, and then we need to be able to pull up those details on demand. So the map gives us the overview, the Spacetime Cube gives us the detail on demand. How do we filter this? WIMP doesn't really apply in AR. We don't have windows, we don't have pointers. So how do we allow navigation in the AR Spacetime Cube space? And this brings up, now that we have 3D UI here, how can we directly interact with AR? We could be using the touchscreen, but again, going back and looking at the literature, it turns out if you use physical interfaces rather than digital ones, it actually encourages users' exploration of that interface and of the space. There's something about actually having that physical object there on the table that users want to pick it up, they want to move it around, they want to explore the space. So let's use tangibles. So what we developed, you can see on the right-hand side there, and this is where we get the name GeoGate from, is we essentially developed this round tangible. We have a number of buttons around the outside that are primarily used for debugging, but we can also do simple primitive things like zoom in and out. We have an Arduino and a battery in the right-hand side there that you can see that's embedded, and then we have a couple of markers on the top that we use to track it with a motion capture system. So what we essentially end up with is a large tabletop display that has our map on it. We then have our tangible device, the GeoGate ring, sitting on top of it. This allows the user to actually focus on a specific region of interest that they want to visualize in the Spacetime Cube. And then for our system, we were using the Microsoft Hololens to actually visualize the AR Spacetime Cube. Now, hopefully everyone's used the Hololens. One thing about it is it's a great AR device, but it still actually has a relatively limited field of view. So what was great about actually having the GeoGate ring there is if we put a virtual frustum coming out of the Spacetime Cube, and we then intersect that with the view frustum from the HoloLens, is we can actually figure out approximately the optimum size that we can actually fit the Spacetime Cube in relative to the HoloLens's field of view. This means when the user actually puts on the device, they're not necessarily expecting to see AR content across the entire tabletop space. It's actually naturally limiting it based on where the GeoGate ring is. What this actually looks like, this is a very early development build. So we can see here we've got the GeoGate ring on the table. As we move it across, the Spacetime Cube moves across with it. The user can then actually rotate that ring and actually see the Spacetime Cube rotate above it as well. So because we are dealing with 3D, we need to orientate it so we can get the best possible view for the angles that we need to minimize occlusion and everything else. I should note there is obviously a bit of a lag there as we're moving the GeoGate device across and then showing the data up there. As I mentioned, this was a development build, so at that point we were streaming everything, including the map textures and all that, to the HoloLens, so we had a little bit of a delay there, but we addressed that in future versions. The issue with this is while you could rotate the tangible to essentially view the Spacetime Cube from the full 360 degrees without having to walk all the way around the table, the issue with that is whilst you've got a fixed north on the map in terms of direction, when you start to rotate this tangible around, it becomes very disorientating in terms of which way the Spacetime Cube is facing relative to the map. So we needed a way to address that. Ooh. So as Red Bull would say, you give it wings. So what we did is for the Spacetime Cube, we've got 5 sides of the cube. We've got the 4 sides that go vertically and then the view on top. So what we decided to do was essentially add virtual cameras to each side of the cube and then show what it looks like if you're viewing the cube from each of those sides and then show that as a 2D visualization around the cube. So on the rear left-hand side of the cube, that's actually showing what it looks like to look at that cube from the left-hand side. On the right-hand side here, that's what it looks like to look from the right hand, and from the front, that's what it looks like if you were to actually go straight down the barrel for the cube. The top-down view is then shown on the front left-hand side of the cube, and on the front right, we actually have what it looks like to look from the rear of the cube looking forward to where the user is. So what this enables us to do is, even though we went to 3D to try and avoid the issues of 2D representation, we can actually present what the cube looks like persistently to the user. It means we don't have this issue where we're actually having to then rotate the Spacetime Cube relative to the map, and the user can link these 5 individual views back to the 3D Spacetime Cube that we've got up the top. So once we had this, we needed to perform a user study to actually figure out, is this worth anything or not? So what we sought out to do was to compare GeoGate against a 2D traditional user interface being a keyboard and mouse. We wanted to compare it against that because that's what it's currently being used in the real world for these kind of problems. We followed a similar methodology to a prior study by Amini et al., where effectively we were getting users to answer multiple choice questions to extract information from a data set. For each multiple choice question, they were given 4 possible options. They could try and answer that question multiple times, up to 3 times. If on the 3rd attempt for that question it was still incorrect, then we forced them to the next question. We had 3 difficulty levels of question, again defined by Amini et al. So we had a number of different data sets. Each data set then had different entities, different timestamps, etc. But fundamentally, the 5 types of questions that we were asking is we wanted to be able to find a trace ID that was associated with something, easy. We want to find a trace ID from a specific location, medium difficulty. Find a trace ID that doesn't have any light data associated with it, medium difficulty. Find the closest light data point among multiple trajectories, class this is hard. And then find light data associated with a specific entity, easy. We had 2 hypotheses. One was that GeoGate would be as fast or faster for understanding the geotemporal movements compared to 2D. The second one was accuracy, that GeoGate would improve the accuracy when correlating movements of these multiple entities compared to the 2D desktop environment. For results, we found that GeoGate was slower for question 2, where the user had to actually relate back to a specific latitude and longitude, but it was as fast for the other questions comparing to 2D. But most importantly, I think GeoGate was actually more accurate for answering the difficult questions correctly and equally as accurate for the others. So it means it was as accurate or better. One interesting observation was there was only hard questions where the 2D desktop condition actually resulted in complete failure, which is 3 consecutive attempts and could not get a correct answer. And we had no complete fails for GeoGate. So we can just see here the significant result for question 2, where it took significantly longer for GeoGate, and based on user feedback, it was rated as much harder to use GeoGate for question 2 than 2D. Sorry, just because I'm running out of time. So for system difficulty, user reported that it was significantly easier using GeoGate to find IDs associated with traces, and it was significantly easier to use the 2D for looking up locations, and users preferred GeoGate for 4 out of 5 questions. The limitation is we don't actually know what it is that caused this result. Was it the Spacetime cube, AR, tabletop, the tangible, or an interaction of these factors? We don't know at this time. So in summary, we expanded the Spacetime cube into AR to address the complexity of correlating these multiple data sets. We had the 5-view enhancement of the STC with multiple views as wings. We had the novel tangible user interface to link the Spacetime cube and the tabletop, and then the integrated tabletop system with everything. And then we found GeoGate was as fast for all but 1 question type and as accurate or better for answering the questions. Thank you.
Thank you, James, for these presentations. Very interesting. Maybe some of the people of the audience can have a question. Yes, we have.
Hi, nice work. I am Luciana from the Federal University of Rio Grande do Sul in Brazil. And have you tested your proposal, the GeoGate, with a lot of data? Because in the examples you have shown, you have the traces, but you can deal with this. When you have more data than this in the same space, how do you do?
At this point in time, we've only focused on the maritime domain. I suppose with the direct application of our research, it was relatively limited in scope in terms of the problem, directly addressing the problem that the agency had. So at this point in time, it's only been kind of with this correlation of discrete data points back to the trajectories. But I think there's definite applications of this kind of outside of that. You know, in terms of the national security space, there's a lot of agencies dealing with surveillance and those kind of domains as well, and I think it has applications to those space, but as yet we haven't explored that yet.
Okay, thank you.
Thank you for the question.
I think we have time for another question. So I think this is I have a question then. So this is an approach using tangible interfaces. So I think this the restricted point of view is because the HoloLens right now has this. So my question is if the data are variable in time, if there is some specific tangible interface that you develop for controlling the time schedule or time general.
So it's an interesting question. Early on, you know, we were exploring how do we explore time. And when we had that initial kind of rotation, the tangible, do we associate that with time? And again, one of the issues that we had was kind of what's intuitive for the user, what's easy for the user. And going back to tangibles being great because users want to explore the space, we found when we associated that with time, it was very hard for users to then kind of focus and get back to the specific time points that they wanted. So we learned quite quickly that at least for the rotation interaction that we shouldn't be associating that with time. In terms of other ways to interact with it, at this point we haven't kind of explored that space too much. For the time frames that we were looking at for this, it was primarily about 24 to 48 hours worth of data. So again, for the limited scope that we were looking at, it wasn't a huge priority for this version, but I think going forward there's definitely applications and ways that you can incorporate tangibles to explore that. But as yet we haven't.
Okay. Thank you very much. We can go to the next presenter.